is the old computer, but we can go to 60. Okay, so today is class 4. Okay, and first I want to give some comments that were missing from last class. Okay. Okay. One of the comments is that you saw this. We use this method, okay, with the equilibrium ratio, where this expression k was somehow measured. Okay, was available from an expression, and then based on that, we did all the development to use the equations in a very convenient way called the Rachford-Rice equation. This one here, and we had just to iterate to find the solution FV. Okay, with the advantage this equation had is that Zi was input, the equilibrium ratio per component Ki was also an input, and then we had just to find the FV. Okay, we just have to iterate with one variable, and then based on that we could find Xi, Yi, and the rest. Okay, and that's a central part on flash calculation, on equilibrium calculation. Now, one thing that we didn't discuss was the expression we use for this case. Okay, this case I mentioned, they are available, so I uploaded for you a new version of the reference material. Okay, and you have one section on these k values. Okay, and it starts here. That's on this the reference material. It's uploaded on my website, and they explain first the chart, the behavior, where you have this linear behavior initially, and then it starts to deviate. Okay, and give some approximations, some expressions that you can use to estimate these values. Okay, and you can read here different approach with time, different people were using different expression, but basically, if we go here, say on this curve, the line for a given component, if you are on the linear region, it depends on that component. Of course, it depends on pressure. Okay, it depends on the temperature. Okay, but it also depends on the component, which component you have. If you have methane, if you have propane, if you have butane. And that dependence, in our case, if we remember the exercise we have done, how did we input that, that dependence? With 3 parameters, okay? What were those? Critical pressure, critical temperature, and eccentric factor. So that's how we give the dependence on the okay, it was here, these 3, they helped me to define that was an input for this Ki. Okay, these 3. Now, on the nonlinear part, when we are going and starting to approach this convergence pressure, okay, remember, fictitious doesn't exist. Only when you are at the critical temperature, you reach that all of them join in the same point. Okay, for all other temperatures, it's going to stop someplace at the bubble point pressure or at the dew point pressure. Okay, it doesn't exist. It's an imaginary curve, but after that point, so let me just make let's make a very fast, very quick plot. Okay. You have here Ki log of Ki. You here have the log of pressure in log scale. Okay, and you had here you have 1, 10, 100, 1,000. And let's say you had these 3. When it starts to have some curvature, okay, when the equation starts to have some curvature, from that point on, the K is basically a function of what we already discussed: pressure, temperature, and the properties of the component. Okay, Pc Tc, and the eccentric factor is omega. But when I'm to the right side, when it starts to get curved, it's also a function. Ki becomes also a function on top of all the other things, Pt, Tc, Pc, and omega. It becomes also a function of what other components are in the same container. Okay, what components you have together. So in other words, it's also a function of set I. Okay, so that means that the way methane behaves, or the way methane splits, and ethane and propane and the rest, depends how many other moles of methane you have, how many other moles of ethane you have, and so forth. Okay, so that's why, to avoid that complication, we have removed that parameter. We know it depends on that, but we create this fictitious pK, okay, this convergence pressure, to try to capture that effect. Okay, and you can actually, practically, you can change that number until you get a match with the data. Okay, so pK is representing the composition dependence. Okay, so just for you to be aware, if I'm in the linear part, it's very easy to handle. If I'm on the curve section, then I introduce this pK. That's why we need it. Okay, and you can read, I recommend you, if you have on a weekend, you don't have anything planned, or you're preparing before going to a party, you just read these pages, and you get an idea of all the different expression and what each person try to make. Okay, in our case, we're using one of the first ones, this Wilson equation, okay, but modified Wilson by including this pK. Okay, that's the equation we are using. So that was one comment I had, and then the other comment is, and we are going to go back to that at the end of the class, okay? Because you need to have some more information before we talk about it. But the Ki from correlation is not 100% accurate. Okay? It's just an approximation of the equilibrium. Okay, to find out the real value, we have to do something slightly more complicated that we are going to see by the end of the class. Okay, so just be aware. Just here you have just a disclaimer. So it's more appropriate for low pressures. And it's related to that dependence, this pK. Okay, let's say if you have 20% of methane, then 1 pK might be fine, but then you have 50% methane, and then that pK you have to change. Okay, and there is no easy method to do that. It's much easier to use an equation of state. That's what we are going to discuss later. Okay, so just keep that in mind. Then the other thing is that we can use flash, so Rashford Rice calculations, or what we call equilibrium calculations, can be used to estimate bubble point pressure we're not moving very much, and dew point pressures. Okay, okay, in principle, they can be used also, and that's something we want, right? We mentioned yesterday the envelope, right? PT for a mixture, multi-component mixture, looks something like that. Okay, So you are very interested to see where you have this jump. Okay, where are you going to change from single phase liquid to mixture, or where are you going to change from gas to a mixture? Okay, so either here or here. So for that, exactly at this point, what can we say about, okay, about all the, remember the equation, let's, bring it from before. How much it was it? HFV is a function of ZI FV. What was the Rachel-Rice function? Ki minus 1 plus 1 minus FV. So it should be just plus 1 below. Okay. So what happens if we are on this bubble point line? What can I say about, let's say, FV, about the equation? What can I say about FV? What is FV? Number of moles of vapor divided by total number of moles, right? Exactly at this line, what do I have? Just the first very small bubble of vapor, right? Everything is liquid here in this area. And then when I'm exactly crossing that line, I have the first incipient bubble coming out of the liquid. Okay? Therefore, in all of this line here, FV is simply equal to 0, no vapor, right? And in all of this line here, in the dew point line, FV should be 1. Okay? So that really helps my calculation. I can just simply, that really is a big help. Now, another thing, what is, at that line, what is XI? Because I have almost no gas, right? I have some gas, but very, very small. The composition of the liquid should be identical to the composition of the mixture, right? So that means Xi should be Zi. And in this line, the opposite things happen. Yi is equal to Zi. Then you're saying, well, you are already specifying too much, right? What are we going to calculate? Okay, actually, what I want to calculate is, by having these conditions, right? Find a P such that this equation is equal to 0. Okay, for both cases. Okay, to find bubble point, to find PV, bubble point pressure, okay, at a given temperature. Then you make, let's make here like a small recipe. Okay, first you make FB is equal to 0, then you say XI is equal to ZI, okay, and then you don't have K, okay, because you're not sure what is this pressure exactly here. You're not sure about that number. That's what you want to calculate, okay, but you want to find P, okay, such that that equation closes, gives you exactly 0, okay, and the same thing with P dew point, okay, PD, those are PD dew point. Let's make it in red, and let's make this one here, that will be PB. Okay, so to find P dew point at a given temperature, okay, I make the mole fraction, vapor mole fraction equal to 1. I make Yi equal to Zi, and then I try to find a pressure such that HFV, again, such that it closes the system of equation. And that's a way I can use to I can how I can use Rutherford-Rice equation to estimate the saturation pressure and the saturation bubble point pressure and dew point pressure. Okay, we're not going to do it in class. I don't know if I don't know if, but just to keep it in mind if you need to do it in the future. Okay, but still you have the limitation that depends on the source of this K. Okay, if I use a correlation, be careful, might not be very accurate. Okay, now we have managed to do a lot of important things, right? We have so for a given for a mixture, okay, with this procedure. Now we are not, we're not talking about that anymore, just with the equilibrium calculation. I am able to estimate, okay, and that's very important. I am able to estimate the fingerprint, the ID of the liquid of the oil and the ID of the gas. Okay, I'm able to calculate if I have an incoming composition, how is it going to split Xi and Yi. And I'm able also to say to calculate the FV, how much vapor I'm going to generate. Okay, that means if I have a separation process, I have here number of moles total, okay, and then I have here number of moles of vapor, a number of moles of liquid. Okay, I can say that with this FV, I can say N vapor simply N total times FV, and N liquid simply N total times 1 minus FV. So it's very powerful. I'm able to find the amounts, how much I'm separating, at the end how much if I repeat the same process through 3 stages. That's what you have to do in the exercise, okay? We're going to go to that very soon. So you can see how much gas and oil I'm separating, the amounts, and not only the amounts, you're able to know what are the properties of that oil and gas. Okay, with the properties, you can use it for sizing, you can use it for calculating velocities, all kind of things that we need in our engineering calculations. Okay, so just as an example, that's what you will have to do in the exercise that I posted actually today. Okay, it's on Blackboard. The delivery is on Blackboard, but it's also on my website. So that's the exercise. It's the same multi-stage separation train that we discussed yesterday. Okay, you have 50 bar, 35 and 1. Okay, very low pressure. And then we have 70 Celsius, 50 and 15.6. Okay, and you have the composition here at the inlet, and you know that the molar flow, someone measured, okay, don't ask me, that's the chemical engineer, okay, someone measured that I had 1 kilomole per second here. So you have to find out the composition of this, okay, all of these separator, liquid and gas, this and this one, this and this one, this and this one, okay, using Rutherford-Rice and this modified Wilson equation. And then you have to estimate actually how much you have at the end here, this Q oil and Q gas. And that's slightly a bit more tricky, okay? How do I calculate? So what is the first step to calculate this QG and QO? Okay, the standard condition rate of oil and gas. Let's take out for now this standard condition, this mystical condition, okay? Let's say talk about how mechanical engineer or chemical engineer talk about it. How do I find the number of moles, right? that I have here and the number of moles that I have here? Well, I come here with this one, right? I calculate the fraction, and then I can calculate the number of vapor and the number of liquid. Okay, then I take again this number of liquid, I have the fraction, and then I can find again once more the number of gas and the number of moles of liquid. Okay, and then I continue like that. The liquid simply will be the number of moles that I have out of that separation stage. But the gas, I have to sum all the gas from all stages. Okay, and I also have to make the composition in that way. I have to account for the number of moles of all components that you have in every stage. So far, so good? Yeah. So that's what, if you see the Excel sheet you have, and that we're going to use slightly today. Okay, so that's why I tried to make it easy for you. It looks complicated, but you have the X and the Y for every stage. Okay, and then you have the FV for every stage, and then I allow you here to track the moles of every component in every stage. Okay, that means on the first stage how many moles of methane, propane, and decane you have. Okay, with these moles you're able at the end to find the number of moles of oil, the number of moles that you have of gas, and then you're able to find the composition. Okay, now if I have the number of moles, how do I take now? Let's go take to the next step. How do I take from the number of moles to a volume? What do I need to make that conversion? Okay, so the question is, how do I find or I convert from number of moles all the way to this Q? Okay, that means in kilomole per second. Okay, how do I change it to standard cubic meter per day? So let's make an intermediate step. Okay, I think you are a bit asleep, and also I'm a bit asleep. So let's make something like that. Okay, one intermediate step. I have here mass flow. How do I change from mass flow to volume flow? Density, right? You got the idea now. How do I change here? I say from kilogram, let's say per second. Okay, how do I change to that to a volume? And you have to say Q will be equal to mass flow divided by the density, if it's of the oil or the density might be of the gas. Okay, whatever rate I'm calculating. Or let's to avoid confusion, let's say here the density at standard conditions. Okay, and of course I have to change also. How do I change from second to days? It's not trivial. I'm asking just to see if you're awake. And what else? You see, I got you. You're falling asleep. Okay, I multiply number of seconds times 24 hours. Okay, seconds in an hour times 24 hours divided by 1 day. Yes? Okay. That's fine. That we know how to do. We divide, so we need something that so far we haven't discussed yet. Okay? You're saying, well, Milan, you gave me a very nice method. I know how to do it, but you haven't talked about how to get properties, thermodynamic properties. You told me how to calculate the splitting, the number of moles, but I have no idea how to estimate, the properties that I actually need to make my calculation. Okay, and we're going to go that very soon. And how do I change from here to here? With the molar mass. Yes, that's, you see, now you see it clearly. You multiply by the molecular weight. So I say that number of moles times the molecular weight will be equal to the mass flow. Okay, so I have to make these two changes, and I have to find the molecular weight of whenever I'm looking at. Remember, I can apply that process no matter where I am. Okay, if I'm here, if I'm here, if I'm here, everywhere. The only thing you have to use the molecular weight of that stream and the density of that stream. Okay, no matter where you are. In this case, I'm asking you to do it here. Okay, so that's where you have to do at those conditions of pressure and temperature. How do I calculate the molecular weight of that mixture? Another trivial question, just checking if you are awake. We have done it before. Is the sum of the weighted average of mole fraction times the molecular weight of each component, right? So the molecular weight of the mixture, the sum I from 1 to n of, depending what do I have, okay? If I have Z molecular weight I, or I might have here xi or yi. Okay, simply a weighted average of the molecular weights. Now let's go to the crucial part of this density. How do we get the density? So the main question we are going to address today, okay, is how do we estimate let's call it maybe fluid properties. What kind of properties do you think besides density? Density is very important. Okay, it tells me the volume it occupies. In terms of this process, okay, it just simply tells you how much I'm going to sell. Okay, so that's defining your salary. You're working on a field, you're making that calculation. If you're selling 100,000 barrels of oil, you're selling 50,000. That's defining how much money you make. So that amount of volume, that density, is extremely, extremely important. Okay, but what else do we need? Could we need also besides density? So we need density, for example. What else do we typically need? Viscosity. Viscosity gives you on the friction, right? To calculate friction loss. When we talk about temperature, a process you probably saw, long time ago when you were in Barnehage in the kindergarten. Okay, they told you that if you have a process, okay, you have 1 and 2. You could say that, what did they tell you? I forgot. So you say that Q, if I have a process where I have heat removed, okay, Q will be the mass flow H2 minus H1, or the opposite, right? Yeah, no, like that. Yes? All of you familiar with that equation? The first law of the thermodynamics in an open system, okay, where you have an inlet and outlet. Okay, what do I need to make that calculation? Let's say a heat exchanger. Okay, what do I need to make that calculation? A property, right? How do I call this property? Enthalpy. Okay, so I need this H, enthalpy. I also might need entropy. Okay, so these are needed for example, analysis of components. Okay, that means heat exchanger. I need a pump, even a piece of pipe, the temperature drop in a pipe. I need this enthalpy, and I need to analyze a compressor, a pipe. Okay. While there is also one more that I like to let's keep it simple, okay? Just this, but one more, that is the conductivity, okay? The thermal conductivity, okay? Because that tells you how good is the heat transfer in the material, in the fluid, and that tells you something about heat transfer, okay? And later in the course, you will see some applications of, or of this law. But just keep in mind, to make your calculation, you need some of these properties. These properties, the first ones that I listed here, they are called thermodynamic properties. And the second part, which are like transport, you see they're related to transport of either, fluid or transport of heat, and they are called thermophysical properties. Okay. So the first type, this one, I can use the procedure I'm going to describe now. You can use to estimate these type of properties. Okay. For the thermophysical properties, you cannot use that process, but you have to use, sometimes you use basically correlation. Okay. And correlation means an equation. People did many measurements in the lab. They did variation of pressure, different pressure and temperature, and they fit an equation. Okay, might be linear equation, might be polynomial equation, all kind of equation. Okay, just to fit the data. Maybe very complicated, might be very simple, but it has no physics whatsoever. It has matching data. Okay, while this one is using, let's put it right here, is using EOS. We made the abbreviation EOS, or an equation of state, which is like an equation that has some physics inside. I can use to calculate those properties. And we are going to focus on that part now first. Our main goal for this class will be to estimate density. Okay, but we can use it to estimate, we will see, to estimate the other things also. Okay. So what do you remember is an easy way to correlate pressure and temperature and density? Do you remember also from your old studies? Ideal gas law, right? And the ideal gas law, just to put some color to the figures, okay, were developed by a bunch of mainly French, okay, French guy, and also some English. It was not a development that happened, overnight. You had Boyle made some observations how the volume changed with pressure. Okay, then came Hooke, who was also helping and making the experiments of Boyle. Charles made the change with temperature, and eventually they finally went and ended up with PV, right? PV is equal nRT. Okay, and that's the ideal gas equation. Now let's look a bit at the units here. Okay, what units do I have for pressure? If I'm talking pure SI, should be Pascal, right? Or if I'm talking, let's say, field units, Norwegian field units, I will say bar, okay, absolute. The volume, what units do I use for volume? Let me just move that to the top. And here we have to be careful, okay? Volume is cubic meter. Okay, N, number of moles, I can use simply moles or kilomole. Okay, T, I use always absolute unit. Okay, always an absolute unit. That means always K, or I can use Rankine if I want. but in SI units is Kelvin. Okay, and R, whatever makes that thing, okay, consistent. Okay, that means R. Okay, R, it's PV, and T, that means that R has units of pressure, cubic meter, mole, and Kelvin. Okay, if you simplify Pascal with cubic meter, then you get joules. Okay, and just to help you with to remember, because for the exercise you might need it, I also uploaded on the reference material. Okay, the monograph of Curtis has a nice table saying what is the gas constant. They call it universal gas constant. It's R. Okay, and depending on the units that you are using, you have a different number. Okay, so depending which units you are using for the rest, you choose your R. Okay, which is very practical. We're going to use, actually, they're not here, but it's similar to on our exercise. We're going to use this one, I think. Okay. Now we know this equation, okay, doesn't work well for, that works well for low pressure and for ideal gas. Okay, when I start to deviate, I get it's not very accurate. Okay, so what do I do to improve the performance of that equation? And that, I guess, you also had it from before, right? I include something called a deviation factor, gas deviation factor, or a gas compressibility factor. Okay, that I use the letter Z. Don't be confused with composition. Is the gas deviation factor Z? P V Z R N Z R T. Okay. Sometimes, to avoid carrying this N here, what I do, I use the V, which is the specific molar volume, okay, which is V divided by N, specific molar volume. Okay, and that's the one, most of the equations you see written with V, ZRT. Now we can use that, and that C is the gas deviation factor or the gas compressibility factor. Okay, and I have added a section of the monograph, the same, where you can read about that C factor. Okay, but basically we have a chart. If I can take a screenshot of this. We're going to see now the limitations of this case. It was a very well and very well spread use equation for many years. And basically I have to enter with two variables. Okay, I have to come with PR, pseudo reduced pressure, which is the pressure divided by the critical pressure of the component or of the mixture. Okay, this said, I can also use it for a mixture, but I have to have this critical temperature and critical pressure of the mixture, which is not trivial. Okay, I have to find a way to do it. And then let's say it's 12. Okay, and then I knock with the line that has these numbers that I have here are the critical temperature, TR, T divided by TC. And if so I have here divided in two sections. because otherwise the chart will be very wide. Okay, but see the bottom part is like an extension of the first part. If you put one next to the other, then you see the scale here. It goes from 7 to 15, okay? And here it goes from 0 to 6 to 8. Okay? So if you overlap the two, you will get just one very large plot. Okay? To make it more compact, they say if you have your PR is in this range, I read this chart. Or if your PR is on that range, then I read on this chart. Okay? But very simple. If I have, assuming that I have, let's say I have methane, I have this PC, I have this TC, I calculate my pseudo-reduced properties, I come and I find set, and I can find very easily density. Okay, remember density is, so I have to divide V. How do I find density from V? Another easy question, just to check if you're awake. Okay, let's look at the units, cubic meter per mole. Okay, so I have to divide by the molecular weight, right? Yes. So I get here cubic meter per kilogram. Okay, and then I have to invert that. So I have to say density V divided by molecular weight to the -1. Correct? You have to do quality control, okay? I might be doing mistake. So you have to do some QC. So that is something, this equation, which is, we call it, that's the ideal gas equation, and that's the real gas equation. Okay, was an improvement, and actually people use it very much together with that chart for petroleum calculations for a very, very long time. Okay, the only issue is when I have a mixture, okay, when having a mixture, so how to estimate PC and TC? Okay, how do I estimate that? So on this chapter that I pointed here, okay, you have C factor correlation. Okay, you have some ways that you don't have to rely on the chart, but you basically can use an equation, and there are many different. There was actually a correlation by, I don't know much how to pronounce that name, but Harl and Yarborough. Okay, and they made an equation that matches very well this chart. So you don't have to use the chart any time. You take out the human factor. But on this critical pressure, okay, critical pressure and temperature, were some researchers, they came after a lot of testing in the lab, they just found, well, I have an expression. If you give me what is that, gamma? Specific gravity, right? And what is that? The specific gravity of the hydrocarbon? I'm quizzing you now on things that we covered last week, okay? So let's take these two expressions. Okay, so they try to find a correlation for this critical pressure and temperature that will be just a function of the specific gravity of the gas. Okay, this equation was mainly used for gas. Okay, so what is gamma? Gamma gas hydrocarbon is the density of the gas at standard conditions, right? Divided by the density of air, right? Also at standard conditions. But that is equal to the molecular weight. If you use the real gas equation, and if you simplify terms, you will see That is the molecular weight of the gas divided by the molecular weight of air. Why? Because at low pressures, I have the ideal gas equation, okay? Ideal gas law. Z is 1 for both equations. The pressure and temperature are the same. I divide both equations. I end up that the ratio of densities is simply the ratio between molecular weights. Okay, what is the molecular weight of air? 28.97, I think. Well, I'm going to put a question mark, okay? You have to verify, I'm not sure. As part of the fun of this class, you have to do some quality control. You have to QC the teacher. Okay. That clear? We're not going to make, that's simple, okay? So we're not going to make any exercise on that. But until, even now, you can use it for your calculation. You're in the middle of the jungle, you have nothing, you are just have this chart, okay? And they ask you, give me the density of the gas, you go and use that equation, okay? This chart with that equation, okay? And work very, very well. We're going to see now a more robust approach that people came to try to improve this equation, and actually that's the working horse of the oil industry up to today. Okay, in reservoir, people working with production, working with drilling, that's what people are using, okay, which is an equation of state. But first, should we take a break? Yeah, okay, let's say 10 minutes break. Okay. So what we use in the for all of our engineering calculations, also in many other engineering areas, we use what is called an equation of state. And basically, because that equation is very simple to use, right? This equation. The problem is to try to define the behavior of Z. Okay, it's relatively easy or easier to make it for gas. Well, when you start to enter into a mixture, that it's really extremely difficult to find a relationship for Z. So people came with an alternative to say, let's try to use an equation that relates explicitly pressure, temperature, and volume. Okay, and that's why sometimes we call PVT. Okay, PVT calculation. Okay, is pressure, volume, and temperature, the three, and they are in the same expression. So one of them, you probably are familiar with it. It was the equation by van der Waals, okay, in 1873, a long time ago. So he came with this improvement. He say, well, you don't have to use, any deviation factor, but if you write the equation like that, it gives you significantly better prediction, which was correct. And a bit the thinking behind the equation was I have what I call an attraction term, okay, and I have a repulsion term. Okay, first, it's not the original equation, okay, P RT over V, okay, over V like that. Remember, this small v is specific molar volume, okay, units are cubic meter per mole or kilomole. Okay, if you see that equation, it's like it has a linear or inverse linear dependency. Okay, so it's very limited. If you have any curvature, okay, then it's any non-linearity is not going to do very well. Okay, by including that term, this v squared, is like it makes it non-linear, so it's able to capture a bit better the reality. Okay, and the other thing is that this is like you have, how you say, if you have higher pressure, you should have more compression, right, of of the substance that you have. But this minus, okay, is essentially removing, like releasing that, is allowing them, the particles, to relax together. Okay, while this one has the opposite effect. It's just simply when I increase the density, okay, it's become more and more packed, the pressure is also increasing. So you have like a relaxing term, you have, in a very simplistic way, you have an attraction and you have repulsion, and these two are competing with each other. Okay, now you also note something. You have some coefficients, okay, of the equation a and b, that you have to make depending on what components you have. Okay, like if you, and that I also have uploaded on the website. Okay, if you go to the chapter 4 that was from before, okay, chapter 4, equation of state, you see here van der Waals, okay, he explains a bit why, the physics behind the equation. Then it tells you how to calculate this a and b. They depend basically on the properties of the substance, the critical pressure, critical temperature, and so forth. Also, so what happens if this equation, I write it, okay, usually I have pressure and temperature. Okay, I want to calculate properties. I want to calculate density, okay, or a specific volume. What do I get if I, just clear V? What kind of equation do I get if I clear V in this expression? Huh? No, not if I clear B, right? Just mathematical expression. I clear, let's say, V minus V, V squared, okay? RT V squared minus A V minus V, okay? And then I have pressure, and then I end up with pressure times V minus V, V squared minus RT V squared plus A V minus V equals 0. Okay, let's say I provide P and T and I want to calculate V. That's a polynomial, right? A polynomial equation. So I have to find the root of that polynomial. Okay, so that's actually what we have to do in real life. Okay, but one way that people found that was slightly easier, okay, they substitute the real gas equation. Okay, they say, well, we can still say that we have this relationship PV Z RT. Okay, but now we are going to substitute everywhere you have V, you substitute Z RT divided by P. Okay, and then I find this set that doesn't come from the chart. Okay, but I'm finding, actually I'm defining that parameter, that set, and that actually makes the equation slightly simpler. And that's the way I'm solving always this equation. That's the equation, and these are the coefficients a and b. It's still polynomial, okay? It's still a cubic order polynomial, okay? But now I make it in such a way that I'm clearing the set instead of the v. So just don't be confused. It's just a different way to solve the equation. If you prefer, you can do it simply with p. It will be still a polynomial, but maybe the constants will be slightly, more difficult. Okay. Now, what happens when I have a mixture with this equation? Okay, you see here you have this A that I had before, but now Z was RT. You introduce this extra term. Okay, so now, yeah, that enters here, and you have to group, and finally you define this big A and big B. Okay, capital A and capital B. But it's essentially the same equation. Okay, it's a polynomial of third order. Now, if I have a mixture, how do I deal with that? If this is a pure component, okay, I have only one PC and one PC. I have to find, okay, an equivalent, these guys, okay, an equivalent A and an equivalent B. for the whole mixture, that represents the whole mixture. And people were looking for a long time exactly how to do that in the best way. And that's what we say, that's what we call mixing rules. Okay? So mixing rules are used to find constants for the equation. For the EOS equation, okay, the equation of state, when there are multi-components. Okay, and mixing rule, we're going to see now just how I combine these two. But you have the idea that I have, different properties, PC, TC for different components, and then I mix them. And in this mixing, I have to add some weight, okay, to how much I have of each. Okay, if I have a lot of methane, that should have more weight than if I have, less methane and so forth. And we're going to Okay, so besides van der Waals, I also recommend you to read that chapter. Okay, another lonely night, you're bored, at home, and then you want to remember. I have to read this material, so you read. But basically, I have a bunch of them. Okay, these are called like third cubic equation of state. I have a whole family people that try to improve the work of van der Waals, and they went and they proposed different expressions. Okay, like you have here from Redlich Wong, I think was from the 50s. Okay, came with a slight improvement. Okay, you see here it's exactly the same, but now V, I just use this expression. Okay, add one more term. Okay, then came a bunch of other person. Pavel Redlich Wong made an improvement on Redlich Wong. Okay, we are going to look at one of the most used equations. Okay, so I say instead of me presenting you all the different equations, all the different constants, the mixing rule, let's do it just for one. Okay, you get the idea how that's done, and then you're able to do it for any other equation. Okay, so let's use this equation, which is one of the most used nowadays for reservoir simulation, production simulation, and drilling simulation. Peng Robinson in 76. Okay, so that's how the equation looks like. Okay. That's how the A and the B look like. They have a slightly different constant, okay, that the van der Waals. But so let's do it with an example, okay? Let's do it with to use that equation to clear the density. Okay, I have pressure and temperature, and I want to find out the density. Okay, so I'm going to open the exercise. Okay, so that's the one we're going to look more in detail, the Peng Robinson, and I'm going to show you more or less what do I have to make for to compute properties with an equation of state. That's Robinson. Okay. The other equation, the Suave-Redlich one, that's also very used, is SRK, and it's slightly different, but they are a bit similar. All of them are cubic equation of state. Okay, so I'm going to open the exercise you have to deliver. Okay, so I'm going to help you a little bit. Okay, and I have here the R. Okay, they are a universal gas constant. Temperature and pressure. We should do that for. For the separation process. Okay. Yesterday we have done for. Let me open the notes for yesterday. Okay, so let's do it for can apply it both for the liquid and for the gas, okay? But they are split and they are separate. So I'm applying it both separate. So what do you want to see? The gas? Let's try the gas, okay? So that composition, that was the first stage, the gas coming out of the first stage. Okay, so let me type that here on the EOS. 0.81955. And the pressure and temperature of the first stage was 50. Here I have to put it in megapascal because the constant, this R is in megapascal. Okay, so just be careful with that. So 5 bar is megapascal is to the power of 6 and bar is to the power of 5. Okay, so it's simply 5 megapascals. The temperature 70 Celsius. How many Kelvin is that? 70 plus 273. You see okay with that size? Yeah. Okay, so we have populated the input, okay, the pressure and temperature, and we have populated the composition. So now let's go to the first step. And here I have all of these are properties of each component, the molecular weight, and we're going to discuss now what this S means. Okay, it's some sort of a correction factor for Peng Robinson. So here to the left, I have put like a recipe. Okay, what do you have to do first? So first we have to calculate this B. Okay, this is for each component. So let me see. I think I programmed that for you. B. Okay. B that will use universal gas constant. I have to block it. TC of that component, I have to block it. And PC of that component. No, I don't have to block because I drag it down. And that equation, if we see what is behind, to be sure that we should be the equation for the B of Peng Robinson. Okay, 0.0778 times R TC divided by PC. Okay, don't fall asleep yet. I still have a lot of things to feel. Okay, now I have to M. Okay, M is a factor that depends on the eccentric factor, this omega. So let's see, M. You also have to make sure that I don't make any mistakes. Okay, eccentric factor, this guy. With this M, I can calculate alpha. Alpha depends on M and depends on TR. So let's see, alpha. Alpha depends on M and depends on TR. And TR is the temperature that I have. I block it, divided by the critical temperature. Okay. Okay, just know that I can make, here I'm making a calculation inside a function. Okay, I'm making two things at the same time. Next step, I did all of that because A requires alpha. Alpha requires M, and M requires the eccentric factor. Okay, so you see in van der Waals, I just had one expression for A and B. Okay, in Peng Robinson, I have to do a lot of steps just to find A. Okay, so now let's calculate this A. A is R. Okay. I have to block it. PC, PC, and alpha. Okay, and it's a very small number. And I hope there are no errors. Otherwise, it will be going to cry trying to find the error. That's why you have to be. Otherwise, I'm going to cry. You're going to cry. Everybody's going to cry. Okay? Next step is this mixture, okay, A and B. You don't have just purely, you don't have purely methane, you have a mixture also with B. So the way this mixing rule, what I mentioned here, okay, the mixing rule, it says that you have to combine them in the following way. For B, it's simply just a weight average with the mole fraction. Very simple, okay? Just multiply the mole fraction times each B. For A is more complicated. You have the A of both, but you have to have two summations. Everybody understands this? Well, you're smart. I had to write this on a piece of paper, okay? 12 sheets, and then I say, oh, I understand now what they are doing, okay? But basically, I start to make a summation first, okay, and then I make the other one. Okay, but you see here you have these two A's, okay, but I have the two compositions, okay. Let's say I do methane, and then I do methane with propane, methane with decay. Stop. Then I make propane with methane, propane with propane, and propane with decay. Okay, so I have a bunch of terms. But what is this beep here? This beep is something that many equation of state has, that is just to improve prediction. They say, we know that it's not exactly ideal, okay? We know if it were ideal, this will be 1, okay? But we know it's not exactly ideal, the combination. So we include this factor, which is like a correction factor, to correct for this non-ideality in the mixing. And this is typically given by a matrix like that. And that tells you that, for example, between propane and methane, there is some interaction. So you have to add some correction terms. Also between methane and decay. Okay? And of course, the ones is symmetric, the matrix. Okay? The interaction between methane and propane should be the same as the interaction between propane and methane. Okay? So that is a problem, right? But I have made so that we have to populate here, okay? A mix and B mix. But I made your life simple. So let's see. A mix, it's this guy, okay? And this function is taking a vector, which is the vector of A's, is taking the vector of compositions, and is taking the matrix of beeps, okay? And then it has four loops, two for loops, okay? Those are the two summations. We're not going to go in detail in class, but when you're solving the exercise, I suggest you take some time to see what is inside. Okay, but basically, it's doing that part. This part here is making that sum, that ugly sum that you have here. Okay, and also for B mix should be it's here. Okay, and that's slightly simpler times composition times the B vector and summing all terms. Okay. So let's see, A mix, and then here I have to be careful. Sorry, it should be A mix. A vector, this guy, okay. The beeps matrix, I have to put only the numbers, okay, and the composition that I have, this composition here. Okay, and I got that number, okay, you see someplace in between these ones, okay, 2.9, and actually it's much closer to methane, okay, and that's why you see you have 81% methane. So most of the substance is made out of methane, so it makes sense that it's close to that number. B mix, B mix, B vector, where I have the B vector, and then the composition. Okay, and the same thing here, 3.23 is very close to the methane. Okay, now let's go back to the right. What else do I have? Okay, still I'm not finished. I have to calculate this A and B. Okay, that this A and B are, you see, are the coefficients of this polynomial. Finally, I reached the equation. That is the equation of state. But you see all the things that I had to do before reaching that. Okay, but I have, so I need this big B, which is B mix times, is like you are making it adimensional. Okay, Z is adimensional, so I should have all coefficients inside should be adimensional. Okay, so it's like a dimension, making it dimensionless. Also here, and finally I have that part. So let's see. For that, I think I already also made an equation for you. Okay, A makes dimensionless and B makes dimensionless. So let's use that equation. A mix, pressure, temperature, and R. Okay, and now I have B mix, dimensionless, B pressure, temperature, and R. Finally, okay, I found this A and B. After I have the A and B, I can calculate each one of these coefficients. Okay, so that's what I'm doing here. The first coefficient is 1. The second coefficient is minus 1 minus B. That's this guy here. Minus 1 minus B. The third coefficient is A minus 3B squared minus 2B. A minus 3B squared minus 2B. The last one is A times B minus B squared minus B to the 3. Okay, so I have found all the coefficients in Z. What's next? We're almost there, right? Almost there. What is the next step? Solve, okay? How do you solve a polynomial, a cubic equation? You thought that you cover in high school, that class in math, you were never going to use it. Who solves cubic equation? Okay, now you got it back. Sorry for that. So for that, I put a link for you. Okay, here, solve cubic equation, where a person gives a procedure how to solve it, and it's not loading. Um, why not? Okay, solution. The name of the article is Solution Techniques for Cubic Equation of State and Root Finding. Okay, so this article, if you want to see how it's done, you want to refresh it. You have an analytical scheme. That's the one we are using here in this Excel sheet. Or you have also numerical scheme, okay, where you use like a Newton-Raphson type. Okay, semi-analytical or analytical. Okay, for this case, we're using the analytical. You want to find the details, you see them there. But basically, I have two options. Okay, I always have two options with this type of equation. If I calculate a factor called m, okay, you can see the details in the link. If this m is less than 0, then I'm going to have three roots. If this m is greater than 0, I just have one unique root. I'm lucky, okay? In this case, I have just one root. Okay, and I'm able to find that root according to that procedure. I found Z. The next step now is, you already forgot what we were doing, right? Okay, we took all of the things we have done just to find this equation to find Z. After I have Z, I have pressure and temperature. What I'm doing, what I'm looking for after all of that? Density. But I cannot calculate directly density. I calculate, no, the molar specific, the specific molar volume, okay? Even I forgot what we were doing, okay? So we have, remember, P, V, ZRT, okay? We have this guy now, we have this guy, we have this guy, and we have this guy. We have everything we need, right? So simply, we have to say V ZRT divided by P. Okay, that's the next equation we are going to use here. Z, select this guy. P, so what was the equation? Z times R, right, times T divided by P. Okay. 5. And be careful, okay? This number is in moles, okay? And this number I put here is in kilomole. How do I change from kilomole to, from mole to kilomole? Okay, I have one expression that gives me 1 over mole, right? And I want to put it in kilomole. So I say 1,000 moles, right, is a kilomole. That means I have to multiply B by 1,000. I think so. Okay, the next step, I have V to calculate density. Okay, remember what was the whole procedure? We have outlined at the beginning of the class. It was a long time back. Okay, we have this guy. We divide, we multiply by molecular weight. Okay, and then yeah, density. The density is here, I think. No. Yeah, this expression. Okay, density is the volume divided by molecular weight. The inverse of that. So first I said here, so I need the molecular weight. What is the molecular weight of that mixture? Is simply, right, the weighted, this fraction times this mole fraction plus this one times this mole fraction plus this guy times this mole fraction. Tells me is 21, and that makes sense. It should be close. I have more methane, so it should be close to methane. 21.3. The V then is this guy divided by the specific volume, that, right? Okay, to give me in cubic meter per kilogram. Then the density is the inverse of that. 41.9. I hope I didn't make any mistake, okay? So we said Z was, I have M is greater than 0. So Z is this number. I put it here. The volume is then Z times R times T divided by P, and I multiply by 1,000 because here R is in moles, okay? And I want the molecular weight is in kilogram per kilomole. So to cancel kilomole should be cancelled with kilomole also. That's why I multiply by 1,000. Okay? And I wanted to change units from cubic meter per kilomole to cubic meter per kilogram. So I simply divide by the molecular weight. Okay, so kilomole gets cancelled above and below. Then finally, I just say the density, well, is just the inverse of the specific volume. Okay, 41.9. That means if someone wants to make calculations at the exit, okay, of my separation process, here exactly, we are looking here, then the density that they should use of the fluid there is 41.42, okay, essentially.
What is the difference between the B and B corrected, or there's
Yeah. So far, more or less okay? Yeah. Are you okay to absorb the last part of the lecture? Yeah. More or less? Okay. Yeah. Okay. Peng Robinson gives a much better prediction of liquid densities, okay? But it's not perfect. So people try to say this is a very nice equation of state, but how can I improve the prediction of just the liquid densities? Okay? So they came up with a way by using this C factor. Okay, they will say my specific volume, molar volume that I the final one will be the one that I obtained from the EOS minus this correction factor. Okay, don't ask how they came up with a guy called Penelux, and he said if you include this term and you subtract it from the EOS volume, you're going to improve much. You're going to get a much better prediction. Okay, and this C is the B that we calculated earlier, right? But and you have an S which is called volume shift. Okay, so just to recap, this value was not okay. Okay, this guy will say for especially for high pressure, high temperature, that value that we obtained just now is not very good. Okay, so he said let's put this correction factor, okay, where this is the mole fraction, and this C is the B multiplied something called a volume shift. Okay, that you see I have it here. S volume shift. So people were trying to find an S that matched a bit better the data, they measured the data in the lab. So if you want, we can do that calculation. It's not too difficult. Well, we have to calculate first C, and C is B times S, okay? So it's very simple. It's simply B times S. And then the correction, how do I apply? I apply the correction. I have to say is the original, right? Minus the sum, this one times this C minus this one times this C minus this one times this C. And remember, this is in kilomole, in mole, so I should multiply by 1,000, all of that. How do I multiply by 1,000? Okay? And you see now the new value that I obtained is, instead of being 506, now I get 511. Okay? And now if this B, I should take actually the corrected. So the density changed from 41.9 to 41.3. Okay? Here it doesn't look like much, but for high pressure, high temperature is significant value. Okay, so that was just to give you a taste. How do you do equation of state calculation with Peng Robinson? Now there is the last thing I wanted to say is that you can also calculate, and let's do it also. You can calculate from the equation of state some sort of is like some sort of an energy, okay, something that they call chemical potential. It's an energy, some sort of an energy that each component has, okay, that is called fugacity, and see like some sort of a chemical potential. Okay, and that's the equation is here at the end. Okay, um so let me just type here, just to make some notes. So let's say here, with the equation of state, one can calculate other properties. Okay, and the other properties might be enthalpy, might be internal energy, might be S. Okay, all other properties that I need. Okay, and how do I do that? Actually, I do use the definition of the property. Okay, like in the case of enthalpy, you know that is U plus P times V. Okay, like you also use sometimes the first law. You say the heat and work, they are the same as the change in internal energy, du q minus w. Okay, delta q minus delta w. And also you use like some fundamental um, relationships between the derivatives, between the derivative of the property. Okay, and like for example, if you do that for internal energy, okay, you end up with an expression that looks like that. Well, it's very bad quality. Okay, so it's du cv dt. Okay, but you find that, for example, if you're working with a Peng Robinson equation of state, you can actually try to estimate that derivative. Okay, you can go and derive that equation that you have here. Okay, it's not going to be pretty, it's going to be very ugly, this equation, but you can try to derive that equation. Okay, dp, you need dp dt with constant volume. Okay, so you can try to derive that dt with constant volume. Okay, and with that, after you have that, you substitute inside that expression, and then you have, with the same a Peng Robinson equation of state, you can find all other properties, most of them, the thermodynamic properties, internal energy, enthalpy, etc. Okay, now you can calculate one property called the chemical energy. Okay, that the chemical energy is this fugacity for each component, okay, Fi, and has that, ugly expression. We are going to finish very soon, so don't be stressed. So why is that property very useful? Because people observe that if you are in a mixture, if you look at one particular component, okay, in the liquid, and one the same component in the vapor, they should have exactly the same fugacity. They should have exactly the same energy. And you can see in a very simplistic way that if you have, let's say you have an interface, right? And you have gas and you have the liquid. If you have more energy in one than the other, okay, let's say that you have more energy in the liquid, okay? FLI and then F, for example, methane in the liquid and methane in the vapor. If you have more energy in the liquid, that means that you have to send more material, send more energy to the gas, okay? And then you have a transfer of material, a transfer of mass from the liquid to the gas. Or it can be the opposite way. You have more energy in the gas than in the liquid, so you have condensation. Okay, so this energy, if you are in equilibrium, forcefully they have to be the same. Forcefully, they have to be the same. Okay, so a part of this why how I can use this equation of state, okay, that we are not going to discuss in class. We don't have time, and it's a bit too complex. Okay, instead of using the k factors that we used before, okay, we try to find a composition in which these two fugacities are the same. Okay, let me just make it very quickly. Okay, if you give me maybe 5 more minutes, we do it very quickly. So let me calculate this fugacity first, this ugly expression. AI AI depends on is a vector, depends on the beeps, composition, and k. Okay, is a counter, okay, this guy here, and I have to freeze a few things here. So this is a, and this one. Fugacity Peng Robinson for the single component, and I have to put a bunch of things here. Pressure, I block it. Set to block it. A of the mixture. This guy, B of the mixture, dimensionless. B of the mixture, E, BI is this guy, the composition, and AI. Okay, 3. So that gives me the fugacity. Okay, 3 is an energy, but it's in units of pressure. 388, 599, and 190. Okay, that's the gas that's just leaving the first stage separator. Okay, if my K values were correct, okay, what should happen? If I now try and simulate the liquid, that these two numbers should be the same, right? For this fugacity for the methane in the liquid phase should be the same as for the vapor. Okay? And if they are not, That means my k factors were not correct. Okay, I have to iterate. So that's not part of the exercise, but just to make you aware of that, I have another. So I can use the equation of state to find k. I can use the equation of state to find k. That means I assume k. Let's make a very short. Assume ki. Okay. Then I run rush for rice. Okay. Then I find xi and yi. Okay. And then with these two, I find the fugacity of the liquid I and the fugacity of the vapor I. And now I compare, okay? Are they equal? If yes, then I have the solution. If not, then I have to go back and assume another set of case. Okay? So far we have said those cases that we calculate with the equation, these are correct. I don't have to do anything else. But now with the equation of state, I have another option. I can calculate the energy of the component in the liquid, the energy component on the vapor, and then I can compare. If they are the same, yes, that assumption that you made is correct. Okay? If not, I have to again assume another case. We are not evaluating that. It's just to give you like a very brief overview of how you're going to be using the process simulator. You're going to be using is doing that inside. Okay, and this is called vapor liquid equilibrium. Vapor liquid equilibrium calculations. Okay, so you don't have to worry about it, but you have to know slightly, roughly, what it's doing on the inside. Okay. What I have shown today, you can go and read chapter 4. It's very well explained, and you can, from there, probably you can solve all your questions you have. Okay. Yes. Before we close, any question? Many questions. That's why you have to practice. Okay. You have to do the exercise to see if you understood. Okay. For next class, please bring the Mariana. She will be teaching, so you have to bring the computer. Okay.